ladies and gentlemen. Hopefully this is the last time I will be doing this. Okay, I will see you tomorrow online, definitely. So I'm looking forward to that. We can go over lots of your questions. All right, at that point, I will be posting an answer key, my answer key to last night's homework. Okay, so you can check those answers. And what we're doing today, okay, is the next section in the textbook, obtaining information from a graph. So we're going to continue talking about domain and range, but I'm going to add a couple things to it, okay? So right now, if you want, you could pause and do the do now, okay, and then take a look at this, but there's a couple things I want to talk about that are really important on the do now, okay, from looking at your homeworks, okay? So the first one is just, this is a review of operations with functions, right? We have here a cubic, right, cubed, and a linear. These are both, their domains are just all real numbers, right? Negative infinity to positive infinity for both of these. So when I go and talk about the domain, that's something I could ask you. We start off with the domain of the originals. That's all real numbers, so we're all set there. Then here they're asking me to multiply these two. So if I want to do that, that's just going to be negative 2x cubed plus 4, and then 3x minus 1, and then you just multiply these two, so you FOIL it. So it's just negative 6x to the 4th minus, plus, just kidding, 2x cubed plus 12x, and then minus 4. Okay, so G, should say H of x times G of x is that polynomial, okay? So it's a positive 6x to the 4th. Now, if you put this in your calculator, you will see that there is no domain restrictions. Also, it doesn't have the two essential domain restrictions that we talked about, right? It's not a radical, and it does not have a fraction with an x in the denominator. So there are no domain restrictions. It's not either of our two special cases. So the domain of this guy, I know I didn't ask, but would just be all real numbers, okay? Negative infinity to positive infinity, in case I ask that, all right? Now, this is the one that I want to talk about. A lot of you on your homework just listed what kind of symmetry this has. Possibly you put it in your graphic calculator to take a look at the graph, but here I want you to be able to do this algebraically. So if I'm asking you to do this algebraically, what you have to remember is, if I'm doing x-axis symmetry, I'm going to negate the y, right? If I'm doing y-axis symmetry, I'm going to negate the x, and if I'm doing origin symmetry, then I'm going to do negative x and negative y, okay? So you need to show me this work. There were quite a few of you that did not show me anything and just wrote an answer, all right? So here, if I test this one, okay, you have negative y, or negative h of x, doesn't matter what you do, just as long as you're doing the test. Then we divide through by negative 1, and we get y equals positive 2x cubed minus 4. So that does not work, okay? So then if I look at x-axis, so no for that one. Then if I look at, y-axis, and I negate the x's, sorry, there's a 2 there. What am I doing? Silliness. Negative 2, and then negative x plus 4. So then when I simplify this and get rid of the parentheses around the x, that means negative x multiplied by itself 3 times, which will become a negative x. So therefore, this becomes a positive 2x cubed, okay? Which means that it's not the same because this has a different sign. So no, right? The 2x squared has a different sign. Then origin symmetry. Negate the y, negate the x, right? So when I take a look at this guy, right, I'm going to this, I already did, right? So that's just this part, right, should be positive 2x cubed plus 4. Then I divide through by negative 1, and I get this, right? So now it's a negative 2x cubed, so I got my first term. But then if I look here, this is not. So this is no again. So does this have any symmetry? It does not. All right, and that's possible. It could fail all 3 tests, okay? So you could fail all of them, you could fail just one, and you could have 2 types of symmetry. It depends. We saw all different types of graphs when we did this the first day, all right? Now, if you take a look at this, this is where we're gonna take a look at a graph, okay? The first thing we've talked about before, right, is domain and range. So that's definitely something that you need to be able to do. Now, if you look, this has arrows, right? That's gonna be super important today, all right? So if I have arrows, this continues increasing, right? And also moving to the left, and then it continues decreasing, but also moving to the right. So if it continues moving right and left, that means our domain is all real numbers. And then also, okay, we have it increasing and decreasing consistently, like at the ends. So this will be all real numbers as well, okay? This is actually called a polynomial function, okay? So this is something we're gonna be graphing in the next unit, all right, and sketching, but this has no domain restrictions, all right? It is just all real numbers, and the range is all real numbers as well, okay? Now, when we go to decreasing and increasing, okay, that's how we're going to describe the graph. Like, where is it decreasing? Where is it increasing, right? And you've done this before when you've talked about slope, right? The line is increasing, the line is decreasing. Now we're going to take a look at some curves. But obviously, this doesn't just increase or decrease, okay? What it has is what we like to call local minimums and maximums, okay? These are basically turning points. Okay, peaks, I like to say, and valleys. Okay, it's where, I should say the point, let's add that in there, sorry. Point where the graph switches direction. And now this is not a very technical term, but it's how you can see it on the actual graph itself, okay? So if you take a look here, we have a local minimum here and another minimum there, right? Because you can see the graph comes down, this is a low point, and then it switches up. So this is a local minimum. Now the reason I'm calling it a local minimum is technically, right, this graph continues to decrease, right? So this is not a minimum value, it's just a local minimum value. So within this part of the graph, this is where it hits a valley or a low point, okay? So it's called a local minimum because the graph continues to decrease at one of its sides, okay? So this is my local minimum. That would give me, I don't know, let's say we have one, let's just make them nice numbers, like negative 1.5, and then, and this is just an estimate, you can estimate them. And then a negative 2.5, let's just say, okay? That's one of our local minimums. And then here we have another one, right, where we would say this is, I'm going over 0.5, let's say, making a nice round number. And then this would be, I don't know, like negative 0.2, let's say. Okay, just an estimate. Okay, that's another minimum. So that would be positive 0.5 and negative 0.2. Okay, then we also have what is called our maximums. So if you look here, this is a high point, right, isn't it? So we would do the same thing here. This is a local max, right? Again, it's called a local max because the graph continues to increase. So these are actually not maximum points, the highest point on the graph. It's just relative to this area, okay? So This, again, I'm going to use kind of the same values because it's similar to this. This would have negative 0.5, okay, and then we would increase to 0.2, right? That would be my x and my y. And then I'm just going to write that in there. And then my other maximum, right, would be, I'm going to go over 1.5, and I'm going to go up like 2.5. Now, oddly enough, these numbers look similar to our minimums, don't they? Well, I wonder why that's the case. If you look at this graph, can you see that this has origin symmetry? If you take this and rotate it, okay, I'm going to do this very carefully, but if I take this and rotate it, do you see how it's exactly the same graph? Okay, so look at mine, and then you can look at yours, all right, if you have it printed out. But this is the same exact graph. It's just everything is rotated 180 degrees, all right? So this has origin symmetry, so therefore the x's and y's for the mins and the maxes are just negated, right? Aren't they? Right? So this one, we negate this to get the second one here, and then we take this positive one, becomes completely negative, and that's my other local maximum, all right? Now, so this also has origin symmetry, all right? Then if you look here, decreasing or increasing. Okay, this is the other thing that we're going to talk about now. So here, describing a graph and how it changes. Okay, so local mins are always points, coordinate pairs, x, y, okay? Then here, when we do increasing and decreasing, always describe increasing and decreasing with domain, okay? Always with domain, okay? And the other thing is, so describe using, always use it domain, and then also always use parentheses. You never use brackets, okay? And that's because when you increase and decrease, okay, so like if we look at this graph, for example, right? If I'm looking from left to right, okay, and you usually read a graph left to right, correct? So if I look here and I start to trace this with my finger, okay, I'm going down, which means this graph is decreasing up until I meet this minimum, okay? Then, as we said, that's where it switches direction. So now this is a minimum. There is no increasing or decreasing. It's a turning point. Then I start to, as I trace it, increase. So this part of the graph is increasing. I'm going to put a little I. Then I hit my next turning point, my maximum. So I'm going to switch directions. So now I'm going to switch to decreasing ever so slightly for that little part. Then I hit another minimum. My second minimum, that's going to be where I turn, and now I start to increase again. And then last but not least, we go up, and then this guy comes down, and it is decreasing, okay? Now, for a domain, we're going off to negative infinity and positive infinity, right, on the sides. So if I look at my domain values, I'm going to use those to describe my domain, okay, where this is increasing and decreasing. So if I look at decreasing, I start here all the way on the left-hand side. There's an arrow. So that starts at negative infinity all the way until negative 1.5. Then you do your union, and then you go to the next spot where you're decreasing, which is from negative 0.5 until positive 0.5. Notice I'm using my domain values of my mins and my maxes. Then I do it again, and I start decreasing again here, starting at 1.5, and then this has no end, right? I don't hit a min or a max, so that means I'm going to go to infinity, okay? So I had 3 spots right here, here, and here, where my graph was decreasing, okay? Now, I look at my other spots, here's where it's increasing, okay? So I'm going to say it increases from a domain value of negative 1.5, until I stop increasing, which is at negative 0.5, union, the next spot I start increasing at 0.5, and then I increase all the way to 1.5, okay? So those are my increasing and decreasing. Notice the unions, you don't have to worry about the brackets. It's always parentheses, because again, at these points, this is where you're turning. You're neither increasing or decreasing at those turning points, so it's always a soft bracket, okay? All right, so we're gonna do the same thing, except on the next graph. So let's take a look at the next guy, all right? Here, let's try another graph. So give the intervals where it's increasing, decreasing, and then we've got this additional one, which is constant, okay? So if I look at this guy, it is, let's see, I want my mins, my local mins and maxes. This is called a piecewise function, which in your textbook, they talked about this. I know they put this on the homework. This is a discontinuous function, right? Because if I trace it, I have to pick up my pencil to get to the next one, all right? Now, I'm not so concerned about it being continuous or discontinuous, but that's what they mean by that when you are checking your answers. If you look at my answer key, I did not emphasize that, all right? So, piecewise function, okay, which means it's just different functions connected to one another, okay, on the same graph. So if I look at this one, I've got kind of like a turning point here. It's just not smooth. At, let's say this is 2, 4, so this was about at 1, I would say. So it's negative 1, 1, right? Then I have here a point of 2, 4. Okay, and then this line kind of starts at what? 3, 2, 3. Okay, so I'm just labeling my points here. You don't have to do that, all right, but I'm just doing that so I can refer to them easily. Find the intervals where the population, so apparently this is a population, was increasing. So if I look here, we can assume these are arrows here, okay? If I gave this to you on a quiz, it would definitely have arrows, but we can assume those have arrows, okay? So if we have here, this is always negative infinity, this is always positive infinity. Remember, I'm going to use my domain values because we're doing increasing, decreasing, and constant, always domain values. So if I look here, this graph, even though it's going off to the left, as I trace it left to right, it's increasing here, right? Then I hit a turning point and then it starts to decrease. But then I hit this minimum here, right? Which is 0, 0, right? That's our parabola. Also, that's our vertex, which we'll talk more about later on in this chapter. But I hit this, then I turn and I start to now increase, right? So this is decreasing. I hit a turning point, then this is increasing here, okay? And then this one, I'm neither increasing or decreasing, right? I'm staying at a constant value, aren't I? So this is a constant, okay? This part of the piecewise is a constant function, okay? So that one, I can say neither increasing or decreasing, but the x values are changing, right? But the graph itself is staying consistent, so we call that a constant, all right, a constant function. So here, we're going to do increasing from negative infinity all the way up as I trace my graph up to negative 1, because remember, we're using domain. Then I go to the next point, then I go down, but then here at this turning point, I start to increase. So I'm going to say we start to increase at 0, and we continue to do that all the way to the x value of 2. All right. Then decreasing, I think we only have one spot where we're decreasing, right? Because if I trace this increasing, then I start to go down at the left side of this parabolic shape. So I go decrease from -1 all the way to an x value of 0. So I only have one. That's fine. You can only have, it's possible to have one area where it's just decreasing, or maybe sometimes it might not be decreasing at all. That's okay too. And then last but not least, our constant here, right, is going to be, we start at a x value of 2, and we continue until positive infinity, okay? So that's my intervals of increasing, decreasing, and constant, all right? Now, this guy is trigonometry, okay? You're gonna see these kind of ideas on your homework. So I don't know why, but they didn't put the x-axis in here. So this is my x-axis. This is my y value, okay? We will be graphing these as well, which seems crazy, but this is trigonometry. We'll be graphing the sine function later on this year, not until second semester, so don't worry about that. But we have everything labeled. Here's my, that's not my y-axis, I'm crazy. My y-axis is right here at 0, right? So there's my x and y. You can write those in. It makes it a little bit easier, okay? I, again, like to, I'm going to assume that this has arrows on the end. Actually, you know what? We'll not assume that. We'll say it begins and ends. So this is going to have a dot at the end, okay? And again, if I gave you a graph, I would make sure to tell you where it begins and ends, okay? Then here are my local mins and maxes, okay? Now, I would actually call these mins and maxes because this graph has an end, but don't worry so much about that, okay? So here, I believe, right, haven't we gone over negative pi? Right, they labeled them down here, sorry about that, but it's negative pi and then -1, right? And then over here, I'm at positive pi, and this is -1. Then here, I'm at 0 and 1. And then this guy is going to be 2 pi and 1. And then this one is -2 pi and 1. Okay? Oops. That should just be 1. All right. So I just labeled these. Now, if we take a look here, right, we're going to talk about domain and range. Okay, so here, if we talk about domain and range, and then I'm going to come back to number 1. Domain, since I said these were filled in circles, there's a beginning and an end. For domain, this should be -2 pi to 2 pi. Okay, and then your range, you can see, right, exists, your whole entire graph exists between y values of -1, and it is increasing, right, and hits a maximum of 1. So those are inclusive brackets, okay? When you're talking domain and range, you have to determine whether or not it's included or not. In this case, it is, okay? Here, I'm asking you to use function notation, okay? So here, I'm telling you that x equals 0. You need to tell me the y values that correspond to that. So if f of 0, if I look at that, when x is 0, what is y? Well, y is 1. So it's really the coordinate pair. When x is 0, y is 1. So you're looking for the corresponding y value. So if I look here, f of -3 over 3 pi over 2, should be positive, sorry. If I look there, that occurs right here, doesn't it? So that value is -3 pi over 2, comma, 0, right? So therefore, if the x value is this, then what's the y value, okay? and that will be 0. And then on the last one, I gave you f of x, right, equals -1. So I switched it, and I'm saying, if I give you the y, what's the x? So if I look here, y equals -1. That happens right here, doesn't it? So it intersects, there's two x values that occur when y is -1. So that would be at -pi and pi, okay? So I'm just giving you x's and y's. You have to read the graph, find the point, and give me the corresponding x or y coordinate, all right? Okay, x and y intercepts. So we've done this before. X intercepts, right, will be where we hit the x-axis. So that would happen 1, 2, 3, 4 times. So this is -3 pi over 2, comma 0. Then the next one would be -pi over 2, comma 0. Right, that guy. Then the next one would be pi over 2, comma 0. And then the last one would be 3 pi over 2, comma 0. If you look, you can hopefully see that this has y-axis symmetry. So can you see how I have the same x-intercepts on the left and the same x-intercepts on the right? It's just a sign that flips, okay? Because this has y-axis symmetry. Okay, so if you figured that out, you could have just figured out the x-intercepts that way. Now the y-intercept, right, is just 0, comma 1, okay? And then how often does this intersect the y equals 1? Well, let's put that in, okay? So here's my line. Y equals 1. Just how many times? That's all you got to tell me. So 1, 2, 3. 3 times. Okay? And then this is the one that is always tricky, okay, for everybody. They want to know for what values of x is f of x greater than 0. So if I look, right, here's where x equals 0. So we want all the times that it's greater than. So that will exist, right, at, let me highlight it here, this part of the graph, that part of the graph, including this. So we have one part, then a second part, and then a third part. And this is on the homework. So you're going to use interval notation. So it is, again, always using domain values. It is above that line, right? This line right here, when from x values of -2 pi all the way to 0. Not including 0 because it's not equal to. Then we start again here, right, at 0 all the way, sorry, not 0. What am I talking about? Negative, hold on, scratch that, guys. -2. This guy should be, sorry, -3 pi over 2, not 0. So from here to there, right, so notice I'm using the x values. Then I start again from -pi over 2 all the way until pi over 2. And then again over here from 3 pi over 2 until 2 pi. Okay? Now, I'm going to change one thing here. Is this value, right, greater than 0? And is it inclusive? Yes, it is. So this should be a bracket, right, on the end there and on the end here. Okay? These guys don't get brackets because those are on the actual line, and we want when it's greater than 0. That's when they're equal to 0. So it's not inclusive for those. Okay? All right. And then back to increasing and decreasing, okay? So increasing or decreasing, you're going to have, right, it decreases here, right? Then we start to increase. We decrease again. And then we start to increase. So decrease, then increase, decrease, and then increase. So increasing will start at negative pi, always a soft bracket, until an x value of 0, right there. Then I go here and I start where I'm increasing again at positive pi, all the way until 2 pi. Okay, now increasing or decreasing. Don't worry about what we did up here. Okay, this is different. Okay, increasing and decreasing never ever, okay, have any brackets, because here is where it stops. It neither increases or decreases. Okay, we don't know what it does from here. All right, so that is always a soft bracket, no matter what. Then state the interval over which the function is increasing or decreasing. So this one is increasing, so that's just a typo. This should be decreasing. Okay, there is no constant part, so I didn't ask that. So if I'm decreasing here, I'm going to start decreasing at negative 2 pi, all the way until negative pi. Union, I decrease again, starting at 0, all the way until pi. Okay? I'm not going to do the last example. Possibly we'll do that tomorrow together, just so we can go over one together. And that's it, guys. Try the homework. And again, check last night's homework with my detailed answer key. And I will see you guys online tomorrow. Have a good one.